Okay, dear students, today I'm going to talk about LED. This is basic introduction on LED. So what is LED? LED is basically light emitting diode. It's a device which gives you light. The definition here written that it is an optoelectronic device which convert electrical energy into light energy. We are surrounded by LEDs in our daily life. We can see there are so many LEDs being used in our daily life. Like you can see there are diagrams. This image you can see there are these all are the LEDs bulb. This is also an LED bulb which we commonly see in our house. The headlights of the car which is containing an LED strip, and the 7-segment display of an calculator, and many devices. So they all contain LED. So now LED is being used in most of the devices which we are using. So we are going to understand how it works. From where does the light come? The symbol of the LED is this one. This is P-type N-type semiconductor. The arrow represents that there is a flow of its light going outside of that LED. That's PN junction diode. Now this is another diagram which you can see here. In this diagram, there is one. When you see the PN any LED, there is a longer end and a short end. The longer one is anode, the positive one, and the shorter is cathode, the negative. Now, what is the construction of LED? So the first thing which you should be knowing that it is a heavily doped forward bias PN junction diode. So you need to understand that it is heavily doped. What happens due to heavily doping? The depletion region forms is become thinner because electrons and holes meet quickly. So the depletion layer becomes thinner, and it works in forward bias. Second thing is that it is made from a translucent semiconductor like gallium arsenide or indium phosphide. Normally we know that semiconductors like diodes are made of silicon or germanium, but here we use semiconductor gallium arsenide and indium phosphide, because if we use silicon or the conventional germaniums, what happen, we get the light not in form of visible light. They mostly the radiation which comes out to belongs to the thermal regions, so you couldn't see it. But if you use gallium arsenide and indium phosphides, we get light in the visible regions. I will explain you later on. Now when we talk about the structure of an LED, so just let me complete this diagram. So this is a general diagram of LED. This is P-type semiconductor. Okay, this is P, and this is N-type semiconductor. Now what happens? What happens here? That this N is connected to negative, P is connected to positive, so current is moving. It's in forward bias condition, as you can see. So to understand, and there you can see this is symbols of the light which is being emitted from this junction. Okay, this part, the light is coming. Now we need to understand how it works. This is basically made of a glass surface so that light can go out of that diode. The upper part, which I showed in the diagram, if you remember, this upper part of this diode. So from where the light comes. Now to understand or to make it easy, I'm going to use another simplified diagram of a LED. So you can see this is a PN junction diode. N side contain majority electron, P side contain majority of the holes. There is a resistance, electrons, and this is connected to the positive terminal, and this is connected to negative, so it is forward bias. Now when it is not in, when the battery is not connected, you remember that there is a depletion layer from N to P, and this acts as a potential barrier and does not allow any electron to go from N to P side. But when we connect when we forward bias it, or we provide the positive terminal with P and N to the negative terminal, so there is electric field setup, due to which the depletion region becomes very thinner, and the electrons are able to move from this region to this side, and they are able to combine. And when the electron and holes combine, in that process they emit light. To understand how this light comes, we need to understand the valence band theory concept. So you always know that there's a conduction band and valence band in the semiconductor, and there's an energy gap which I'm denoting it here by Eg. So balanced conduction band contains the free electrons which can conduct, or which are the major conductors for that semiconductor, and the valence band contains the holes. Now whenever an electron jump from this conduction band to holes to combine, so it gives us energy in form of radiation, which is equal to the energy gap between the conduction band and valence band. And if the energy gap is suppose Eg, and it is releasing a photon of energy h nu, so h nu equal to Eg, we can simply say, and this will give you a frequency Eg by h. Now this will be the frequency of light which is being emitted. Now if this light happens to be in the visible region, then we can see it, and that's why we use that gallium arsenide, because for that semiconductor the energy band gap correspond to our visible region. So basic thing is this, the basic simple is that when the electron combines, they give the light. Now the color of light emitted depends upon the band energy gap, because if the band gap will be more, it will give you more energy, so the light will belong to like violet or blue, because they have more energy. And if the band gap is small, say, and it is lying in the visible region, so it will belong to the red color. So the color of light emitted depends upon its band energy gap. That's one thing. Second, that intensity is determined by the forward current. More the forward current, more is the intensity of the light emitted. For example, I've taken gallium arsenide phosphate, and the energy gap for this is 1.9 electron volt. And if I put here 1.9 electron volt and divide it by Planck constant, the frequency corresponds to red light. So if we are using a semiconductor of gallium arsenide phosphide, you will get this for red light. But if you are using silicon and things, then you are getting light in that thermal region which we cannot see it. So we are not able to observe this light. So therefore, we use this kind of semiconductor so that we can see the light lies in the visible region. This is the graph of IV characteristic graph. It's just normal to the PN junction forward bias condition. In the forward bias, you get the graph with increasing slope. So same kind of graph is here, but you can see the different color, red, yellow, green. They give different kind of, there is a curve, there is slightly difference, because for different color, you can say they have slightly more barrier potential. For different color, the barrier potential difference, you get a little bit difference in their graph, but the graph is normally like you get in the forward bias, so similar kind of graph you get. Now what is the advantage of LED? So the advantage of LED is that it's low operation voltage and less power. So like it's required very low voltage to operate. Power consumption is less in that case. It's fast action, because once you connect it, electrical setup, and the electron start moving and combining, and it's a fast process. Bandwidth of emitted light is 100 to 500 angstrom. The light which you give is in between this angstrom, and you can suitably choose material and get a monochromatic light of different kinds. Second thing is the advantage of LED is its long life, because it can run for a longer time, because there is no heating of any elements and like that, so it can be used for a longer time. So this is the benefits of LED over the conventional sources, because we are using like the bulbs which we were using earlier, incandescent bulb. So they basically they work on heating an element. So in heating, it's require lots of energy, and essentially the voltage and power are used. So it's not going to be cost efficient, but this LED has a better, because they requires very low voltage to operate. So these are the few advantages of LED, and that's why it's being popular all over the world. And that's for today. Thank you.